Hi everyone, this is Worksheet 1.2, a microscopic description of pressure and partial pressures. And to begin, I'd like to give you the definition of pressure. Maybe you remember this from physics. What pressure is it is a force applied over an area. So that means that one natural unit of pressure is going to be a Newton, which is the unit of force, divided by some sort of maybe meters squared, something like that. And what this unit is this is the Pascal. And you might encounter Pascals in some of your problems that you have to solve. Most of the time we like to deal with atmospheres, torr, bar. There are a lot of pressure units. But Pascals are nice because they're in units of newtons and joules. By the way, the unit of pressure that involves joules is units of energy per volume. So it's going to be joules per meter cubed, and that is also a Pascal. And what pressure means in the context of physical chemistry is we have a wall of the system, and if we say that wall has area A, then there are going to be particles that are moving along with a certain velocity, and they're going to strike the wall and bounce off. And when they bounce off, they impose force on the wall for that short period of time. And obviously, lots and lots of particles hitting the wall with a great amount of frequency seems to impart a relatively constant amount of force against that wall. And so here, let me draw the force vector pointing in that direction. And the combined force applied by all the particles on the wall gives us the pressure. Now, the force caused by one individual particle is going to be the change in momentum of the particle divided by the change in time. And the symbol delta represents change, remember, and then the symbol little p represents momentum, in contrast to big P, which represents pressure. And then down below here, we'll have a change in little t, because little t by convention means time, in contrast to big T, which represents temperature. And what momentum is momentum is going to be the mass of the particle times velocity. Hopefully you remember that from your physics class. Now let's talk about partial pressures and how they relate to mole fractions. So if I've got a sample of dry air, then what the air is going to be made of is approximately 78.08% nitrogen gas. It's going to have 20.95% oxygen gas, 0.93% argon gas, and 0.04% CO2. Now, in order to get the mole fraction from the percentage, you just divide each number by 100. So if I divide 78.08 by 100, I get 0.7808. If I do the same to oxygen, I'm going to get 0.2095. And then for argon, 0.0093. And CO2, 0.0004. Now, the way to relate the mole fraction to the number of moles of each of these gases in the system is to take, in the case of nitrogen gas, the number of moles of nitrogen gas divided by the total number of moles of air, of any of the gas molecules. Similarly with oxygen, it's going to be the number of moles of oxygen divided by the number of moles of air, and the number of moles of argon divided by the number of moles of air gives you the mole fraction of argon, and the number of moles of CO2 divided by the number of moles of air gives you the mole fraction for CO2. And then down here, hopefully it would make sense for you to realize that if you add up all of the mole fractions, then it's going to equal 1. And that's because all the fractions of all the parts are going to add up to equal 1. And hopefully it's also clear that the number of moles of N2 plus the number of moles of O2 plus the number of moles of argon plus the number of moles of CO2 all equal the total number of moles of air. And obviously we are neglecting trace gases in this instance. Okay, flipping over the worksheet, we can use this information to calculate the number of moles of each gas that we have in the mixture. So if I have 0.3 moles of dry air in total, then using the numbers I had before, how do I calculate the number of moles of each component? Well, the number of moles of N2 is going to equal the number of moles of air times the mole fraction of N2. And so if we look back, we get 0.3 moles of air times the mole fraction of N2, which is 0.7808. And if you put that into your calculator, it turns out to be 0.2342. Why don't you stop the video, pause the video for a moment, and try out this part of the problem yourself. Okay, I'm assuming that you've unpaused. The way that you do this is, again, you write down the number of moles of air times the mole fraction of O2. And we've got 3 moles of air, same as before, and 0.2095 for the mole fraction, and that's unitless, by the way, for the mole fraction of oxygen gas, which results in 0.06285. And we probably ought to watch out for sig figs as we're doing these problems. And since I have only one sig fig here for the moles of air, then I really ought to underline these digits right here in order to indicate that that's the proper number of sig figs that the answer should have. Okay, let's fill out this sentence here. In an ideal gas mixture, the pressures, or partial pressures, of the individual gases add up to make the total pressure of the mixture. Okay, so what that means mathematically is that my pressure of the air, or of the whole system, really, that's a mixture of gases, is equal to the partial pressure of the nitrogen gas plus the partial pressure of the oxygen gas plus the partial pressure of the argon gas plus the partial pressure of CO2. And the way that we get the pressure of, say, just the nitrogen gas is we take the mole fraction of the nitrogen gas and multiply it times the total pressure of the air. Same with the oxygen. Mole fraction of the oxygen gas times the pressure of the air. Mole fraction of the argon gas times the pressure of the air. And the mole fraction of the CO2 times the pressure of the air. So that's how you can find each of these quantities. And then down here, there's sort of a shorthand notation where this symbol sigma, this is the Greek letter sigma with an I underneath it, indicates that you, for each partial pressure I, when you sum them all up, then you get the total pressure of the air. So that concludes our discussion of pressures and partial pressures. Please feel free to visit my office hours as usual if you have any questions, and hopefully this will come in handy for your homework. I'll see you later.